Okay, Bismillahirrahmanirrahim. Everyone. So for today, we just proceed with chapter 5 for the discussion of the tutorial question. We will continue the discussion next Wednesday, inshallah. Okay, so for today, today is the 5th chapter of this subject, is Digital Modulation Radio. So there are 6 chapters in this subject, and this is the second last. So Digital Modulation Radio. And today motivational quote is Allah does not intend to make difficulty for you, but He intends to purify you and complete His favor upon you that you may be grateful. From Surah Al-Ma'idah ayat 6. Okay, so until now you already learn 4 chapters in this subject. So for the first chapter, what is the first chapter that you have learned? What is the keyword that important that you need to know in the first chapter? They're included in your first test. So in the first chapter, you have learned the introduction of communication. So there are you have learned about the signal, because in communication the important is we have signal in our world. So so that's why the pre-acquisition of this subject is signal and system. That before you learn this subject, you already learn about subject signal and system. So you already know the background of the signal and system. And in this subject, it's more toward modulation for principal this means in engineering communication. So for the first is important for you to know the difference of analog and digital. Yes, we have the analog signal and we also have the digital signal. And then from analog and digital signal, we have the analog and digital system. So and also you have learned about the component in communication, that we have the transmitter, channel, and then receiver. So for all system, that's for all modulation, for amplitude, frequency, phase, pulse. So all of this is go through all these block diagram, but different modulation have different process. So also in the chapter 1, you already learned about noise. So because in our this means for you to transmit the signal from one place to another place, or one device to another device, it's go through the that means there are internal and external noise. that we have to consider in our system. So there are the keyword that you need to know in chapter 1. And for chapter 2 is about the amplitude modulation. For the first modulation that you have learned is about amplitude modulation. And for amplitude modulation, it's change the amplitude of the carrier signal based on the modulating signal. So in the amplitude modulation, they also have different types of the amplitude modulation based on the, that means the basic, and then it's improve, it's improve the modulation system. For example, we have the DSBFC, the basic one, that is the amplitude modulation. That's we, when we talk about AM, BAM is about the SBFC. And then we have the DSB suppressed carrier. So because when the basic amplitude modulation have many noise and reduce the efficiency, and also the increase the power also, because we also transmit the carrier. So it's why we have the DSPSP, the carrier, no need to transmit in the modulation process. And then the sideband also same, so we have the SSBFC, and the last one is VSB. So all of this is about the amplitude modulation. And for every system, we have the that's mean in the transmitter. Transmitter is the generation. How to generate it, and that's mean in the transmitter, and then how you receive it, and the receive is demodulation. For every modulation, we have this go through all this. So we have the plot diagram for the generation and demodulation, and also for all system also have noise. So you need to this means this is the basic that we go through for all the modulation. And the second one is the FM and PM. This means from angle. This one is angle modulation. Angle modulation. We have the frequency modulation and phase modulation based on the equation that is at the back of the equation. So same also, we have the generation and demodulation of the FM. And also for the FM, we have wideband and narrow band. And also for the generation, there are direct and indirect. So you need to differentiate it, which one, which system can do for the direct and indirect. So the previous chapter that I've learned is pulse modulation. Okay, for okay, this one for pulse modulation, and for AM, for AM and FM, the VMT is analog, but for the pulse, the okay for the this mean okay for the analog and for the analog and AM and FM, the VMT and VCT, the carrier signal is analog signal, amplitude and frequency. The VMT and VCT is analog signal. But for the pulse modulation, the VMT is analog signal, but VCT is the pulse. That means the digital signal. Okay, so this is the difference of AM and the AM, FM, PM and pulse modulation. So this is the pulse modulation. So because of this one, it cannot go through the Wi-Fi because it is digital, so need the transmission. So for today, we proceed with digital modulation radio. Okay, so digital modulation radio is another modulation process. So from this one, this is AM, FM and PM. This is pulse modulation. And for digital modulation, the VMT is the digital, but the VCT is analog. Okay, so this is the difference between pulse modulation and digital modulation. So that means the digital modulation, the input or the original signal or the modulating signal is digital signal. Okay, so this you already learned. So for digital signal, there are three types of digital modulation. There is amplitude shift keying, SK is shift keying, frequency shift keying, and phase shift keying. Okay, the introduction to the digital modulation. Okay, for the pulse signal from the previous modulation or coding method normally are not transmitted in their original form. So they will modulate a carrier that's suitable with channel use. Okay, this is what I mentioned previously, that the pulse signal cannot travel through wireless or free space. Pulse signal cannot travel through wireless or free space, but digital signal can also be transmitted through free space if the analog carrier signal is used. So because the pulse signal, the carrier is the pulse. This means it's changed from analog to the pulse signal by multiplying the analog with the sampler. So it cannot travel through wireless or free space. It's need wired. It's need cable. So there is one of the limitation of the pulse modulation. So for digital modulation, it's that means the digital signal of the modulating signal is multiplied by the carrier signal. They are analog. So when the analog carrier signal is used, it can be transmitted through the free space. So in digital modulation, the signal information is in digital signal, while the carrier is high frequency sinusoidal signal. So the carrier here, the VCT here, same as in amplitude modulation and angle modulation. Just the input or the modulating signal is different. The modulating signal is digital signal. Okay, digital modulation is used to transfer a digital bit stream over an analog channel at high frequency. This modulation technique is similar to the analog modulation, in which the modulating signal will vary the amplitude, frequency, or phase of the carrier signal. The only difference is that the modulating signal is digital signal. Okay, so for this one, it will vary amplitude, frequency, or phase. That means it's almost similar with the AM, FM, and PM. But for this digital modulation, it will call as ASK, amplitude shift keying, FSK, frequency shift keying, and PSK, phase shift keying. So the shift keying is that means switching. The previous term is switching, but that means the shift keying means it's convert to okay, it's a term for this process, shift keying. Okay, and in digital communication, the modulating process involves switching or keying. Okay, this one. The modulation process involves switching or keying the amplitude, frequency, or phase of the carrier in accordance with the input data. And depending on whether of the carrier signal is varied in accordance with the digital message signal, there are three techniques of digital modulation called amplitude shift keying, frequency shift keying, and phase shift keying, as I mentioned just now. Okay, this is the overview how the ASK, FSK, and PSK will look like. Okay, historically, the term shift keying refer to breaking a circuit using a key to shift current value from 0 to 1. This means the term shift keying like breaking the circuit. That's from 0, 1 based on the digital signal. Okay, this is the base signal, baseband digital message signal, MT. As I mentioned before, the modulating signal for digital modulation is digital signal. So digital signal, we don't have the varied amplitude, but we only have two amplitude. There is high and low. High is 1 and low is 0. So the digital signal is this, and then the carrier signal, same as before in amplitude modulation, frequency modulation, and phase modulation. We have the this one EC or AC. This is the carrier signal, the high frequency analog signal. Okay, and for ASK, the message signal change the carrier amplitude because it's the name is amplitude shift keying. So the amplitude, this is the message signal. This is the carrier signal. So the message signal change the carrier amplitude. So it will for the high. This means 1 0 1 0. It will become the amplitude of 1 is high and amplitude of 0 is low. So the amplitude is changing based on the digital signal input. And for the second, frequency shift keying, as similar as frequency modulation, the frequency of the signal will change. So for FS, the frequency, this means for 1, the high frequency is high, and for 0 low, the frequency is low. So same as similar as FM, but this one is the uh, the carrier is follow the one here. Okay, and the third type is phase shift keying. The message signal change the carrier phase. It's almost similar as phase modulation. So it's change the phase of the signal. So there are changes of phase there. Okay. So we proceed with the first type of digital modulation. So for this type of modulation, we present the binary value with two amplitude. The amplitude of 0 for bit 0 and maximum amplitude of carrier for bit 1. Okay, the information signal is form of binary. The BMT is 0101 and the carrier is high frequency signal. The ASK generation is found by multiplying the two signal. So the how to generate the ASK is simple as multiply these two signal, multiply the carrier with the modulating signal. We have the modulating signal, the digital signal, binary, and the carrier high frequency signal. Just multiply it, we will get the VSK. This is how the generation process of the ASK. And mathematical analysis of this generation is this is the formula for digital signal. So and then VCT is EC cos omega CT, and the carrier frequency is higher. This most higher than the modulating frequency. So it's just multiply VCT with the BMT. Okay, so in ASK technique, digital signal is used to switch the carrier amplitude. So, for example, okay, we have the carrier signal, high frequency sinusoidal or high frequency analog signal, and then the modulating signal. So after multiply both together, we will have the result is ASK, amplitude shift keying. When it's 1, it's have the amplitude, but if 0, it's just linear. So also 1 it's become like this. Okay, this is the time domain signal. So for the frequency spectrum of the frequency domain, for this one we have the frequency of FC or omega C. So the frequency spectrum of the carrier is like this, and then the frequency spectrum of modulating signal because it have three high frequency here, 1 value. So we have 3 value. So after multiply, it will become like this. That's it will have at the upper sideband and lower sideband. So this is the frequency spectrum of the ASK. So there are two methods to generate the ASK. There is the multiplier as mentioned in the equation before. So that means for the equation just now is based on the multiplier process of the generation. And the second one is on off switch. So the first one use multiplier, and the second one use the switch. Before the switch, for switch, the switch is open if binary is value 1 and closed if the binary signal is value 0. So if because we have for example 1010, so if it's 1, switch is open, and when it's 0, switch close. Okay, so if this means if 1 is allow the carrier frequency to go through it, so we have the output of the carrier frequency based on carrier frequency, and when the 0, switch is closed, so nothing can go through, and with when it's switch, this when the value is 1, it's switch open, so there will the carrier frequency can go through it. Okay, like this. So okay, after, so this is the VMT. Okay, before that, this symbol is referred to the LPF. This means for the multiplier will pass through a low pass filter first to filter out high frequency. So okay, so because the VCT is high frequency signal, so that's why for the VMT it's go through the low pass filter first to only accept the low frequency signal, and then it's multiplied by the high frequency signal from the carrier frequency. So we will have the VSK. And for on off switch, so this is the symbol of switch, and this is symbol of band pass filter. Okay, so the signal will pass through the band pass filter with limit the bandwidth of the signal. So it select certain range of the signal and multiply with the VCT, with the local oscillator, and then we will have also VSK. Okay, so this is the generation block diagram of the generation of ASK for the by using multiplier, we need the low pass filter, and for the switch, we need the band pass filter. Okay, and at the receiver, so we need to recover the original signal. So from this one, we already have the VSK is like this. Okay, so there are two methods to get back the original signal. That is the digital signal. So first is by using envelope detector, and second by using coherent detector. Okay, for by using the envelope detector, it consists of rectifier. This is rectifier, and low pass filter. Okay, so for the rectifier, we will, okay, this rectifier is only allow the signal from positive pipe. This means only positive pipe go through it. So after going through the rectifier, it will become like this. So only positive. Okay, so this means only allow positive part of the signal, and then it's go through the low pass filter. Okay, so this is the high frequency signal, because this is from the carrier frequency, and after go through the low pass filter, it will become like this, because it's only allow the low frequency signal. So we all already get the digital signal again at the receiver by using envelope detector. So the second method is by using the coherent detector, or another term for this is synchronous detector. And this detector require an oscillator. So this is a local oscillator where the frequency is set to the carrier wave frequency, and that is the modulated signal SK. We undergo the process of multiplication with oscillator, so it's multiplied with another high frequency of the from the local oscillator, and so output of this is a harmonic signal, which consists of the oscillator signal and the ASK modulated signal. Okay, so for this one, Okay, for this one, it's also go through the low pass filter, and okay, for this one, the VST, and then okay, for this high frequency, like this. Okay, so after multiply it, we will get the because so okay, when okay, for this one we have like this from the VASK, and then when we multiply with the local oscillator, we will have the high frequency. That means for the here it's very high, and then when go through the low pass filter, it's only allowed the low frequency. So this is lower than the zero before. So after go through it, can get the VMP again. Okay, so this is the process of the how to get back the digital signal from the VASK. Okay, for the bandwidth and another parameter that is important in signal is the bandwidth of the signal. For ASK, the bandwidth is depending on the information signal. Okay, if the information signal is periodic, that means it have for example 01 101010 or 010101. It is a periodic signal. So the bandwidth is 5 FB. But if it is non-periodic, for example, like 010010, the bandwidth is FB. Okay, why like this? Okay, for example, for 101010, okay, this is the BMP, and this is the time domain for BMP, and then after multiply by the VCT, it will become like this. That means the maximum of, because after multiply by carrier signal, the frequency spectrum become like this. That we have the VCT here, and then 1, 2, 3, 4. Okay, 1, 2, 3, 4. So include the VCT. There are five signal. This means this is the normal for the periodic signal. This means this is the limit. There are no other signal after FC plus 7 FM. So this is the limit for the periodic signal. And then the power spectrum become like this. But okay, this is for periodic. But for non-periodic, For non-periodic, for example, we have 0, 1, 1, 0, 1, 1, 1, like this. Okay, so this one, it will become this will become, we have the FC, and then only two another sideband. So the bandwidth, okay, for this one, the bandwidth is include all. So the value is 5 FP. But for non-periodic, it's only take the maximum peak. So the bandwidth for non-periodic only take this region. So this region is FB, where FB is equal to FM. So this is equal to FM. So this is equal because FM is the maximum of the modulating signal. So this is the FC, and usually this is FC plus FM. This is FC minus FM. So that's why for the non-periodic, the bandwidth is 2 FM. Okay. Okay, proceed with the noise in ASK. So, noise or error in digital communication is measured using bit error rate. So, bit error rate, or we also call it as BER, bit error rate. So, bit error rate is measured based on the differences between the send and receive bit in periodic TO. So, same as this means similar as previous noise. Is the noise is based on the differences between the sent or transmitted and received. So for noise in ASK, it depends on other factors such as modulating technique and also SNR. SNR as in chapter 1, the signal noise ratio. But for digital, it is EB over NO. So the formula for signal noise ratio is EB, that is energy per bit, over noise spectrum. Okay, so this is formula for SNR, and formula for bit error rate or possibility error is PE equal to half of ERFC, a square root of EB over 4NO. Okay, ERFC is, okay, usually in your test or final, it will give tables. This means same as table in the Bessel formula. This means it's give table. The table is the table is like this. So ERFC is error function. ERFC is error function. So it's given the X the X, and then ERFC of X. So you need to refer to this table to get the value of ERFC. So the formula is PE equal half of ERFC square root of EB over 4NO. Okay, EB here is energy per bit. The equation is EC squared T, where the EC is EPP or the peak to peak value over 2. T here is period, time period, like this, time period. And NO here is the noise spectrum density per band. Okay, you need to measure it is per band. It's the noise power per band. So, and then this one is ERFCX value to appendix D. Okay, so okay, we proceed with example first. Okay, can you try to solve this first?
Okay.
Okay, try for 10 minutes. If you want to, okay, you jot down this equation first because you will need to use this equation. Okay, wait a minute, I share it with you. Okay, any question for this? So you need to solve the equation in the bracket first. That's mean in the square root first. After that, you go to the table to check the value based on what is the value of the square root. So we will get the BER or the PE is 2.035 times 10 power of negative 4. Any question until now? So, yes, Winnie?
No question.
No question. Oh, okay. So, that is for the ASK. So, for ASK, you need to know there is the carrier frequency or the carrier signal follow the modulating signal in the this means the based on the carrier frequency of the digital signal. So you need to know that is the for generation we can use the multiplexer and switch on or switch to get the to get the ASK signal. And then when we receive it, you can use the envelope detector or you can use the coherent detector. That's one for the receiver and the bandwidth of the signal, bandwidth of the ASK is based on the information signal. This means if it's periodic, we need to take the formula of 5FB. This means the FB is the two times of the maximum frequency. And if it is non-periodic, just take as FB. That means the bandwidth is FB, where the FB is equal to 2 FM max. And then the noise of the signal. So in the digital, we use BER, that is bit error rate, because in digital signal, the signal is transmit based on the bit. So as here we have the formula for the BER, and okay, this is the formula for BER to find the noise in the digital signal. Okay. We proceed with the FSK. Okay, maybe I will go faster. Okay, for the second technique, second digital modulation is frequency shift keying. Okay, frequency shift keying is it means the frequency of the signal is based on the input, same as ASK, but here the one high frequency, zero low frequency. Okay, and the spectrum for um, if the ASK is only use one carrier signal, but for FSK it's use two carrier signal. So we have the first carrier and the second carrier. This means for the uh, first carrier, the frequency spectrum is become like this, and the second frequency is become this means the second band of the frequency. And for the FSK, the generation of FSK at the transmitter can be achieved by generating two ASK and then adding them. So this is one ASK and this is two ASK, and we will add these two to get the FSK. This is how the FSK modulating signal is produced. So for first ASK, we will have the signal of for first FSK, we will have the signal and then multiply with the digital signal, and we will have the first ASK and then the second ASK. So when it add, it will become like this. So this is the signal for this is the spectrum for digital signal. So when we combine together, this is from the first ASK and this is from second ASK. So for FSK, it combination of two ASK. Okay, how it's look like? It's for example here. Okay. Okay, for this one, for FSK, actually this for the modulating signal here, it is 101. Okay, so what you need to understand that the output should be, this is high and this is low and high again. Okay, so this is the output, but how to get this is, okay, for the this means this is the digital input. We have 101 and okay, first we go through to get the first ASK. This is the first ASK. It will multiply by the VCT here. Multiply it and we will have the first ASK here, 101. And then it's go through the inverter. We will have 0, 1, 0. Okay, when we have the 0, 1, 0, it will multiply by second carrier signal. Okay, this is VC1 and VC2. Okay, for VC1, because VC1 is it's multiplied by the real VMT, so it is this means the FC1 is higher than FC2 because the frequency of carrier frequency 1 is higher than this. So after after multiply the VC2 with modulating signal that is inverted, so it will get this like this 0, 1, 0, but the frequency is lower than the FC1. So it will produce the FSK, which is adding of ASK1 and ASK2. Okay, so this is the basic how the FSK is generated. This means add two ASK. So same like before. This means here V1 is the real, this is the original modulating signal, and V2 is inverted, and VC1 is higher than VC2. So this is the basic mathematical analysis how FSK is generated. So this is the formula of digital signal. And this is inverted. So when it multiply, it's multiply first to get the ASK, and then it's add together. So the mathematical equation is become like this. Okay, for the bandwidth. Okay, for the bandwidth, for ASK, it take until 5, right? But for FSK, it's up to 3 harmonic. Okay, because for example here, we have frequency 1 and frequency 2, and it will consider the third harmonic frequency for the FSK. But for the basic requirement, just follow the bandwidth of the FSK is from here to here. So the formula is FB plus 2 delta F. Okay, FB actually is because FB is 2 F max. So it is like this is FB, and this is FM and another FM. 1 FM, 2 FM, so there is 2. And delta 2 delta F is like from here, from C1 until C2. So 2 delta F is here. So the full bandwidth is follow this equation. So this means 2 FM plus 2 delta F, where the delta F formula is FC1 plus FC2 minus FC1 over 2. So this is the delta F, but you need to multiply by 2. Okay, this is the bandwidth.
Doctor.
Yeah.
For the bandwidth, the formula that is for the third harmonic. It is for the signal that has 3 harmonic or low, 3 or lower than that. Like if it has a second, third, and then we can use the formula.
Because for FSK, it's not depend on the information signal. For ASK, it's depend on the information. That means if it's periodic or non-periodic. There are two type of bandwidth. But for FSK, it's only consider until third harmonic, and then um, the basic formula that you need to follow is FB plus 2 delta F.
Oh, so that
So
means
just follow
we don't have to use the
just follow
formula
the F.
3 times FP plus 2 delta F.
No,
Oh,
no. Just use the FB plus 2 delta F. That three harmonic is considered for the to draw the signal. But if just ask for the bandwidth, so just follow the FB plus 2 delta F. Just follow that formula. That is for the FSK. Okay. So like ASK, we can generate the FSK by multiplier and switch. But there another method is use VCO. So for the multiplier, same as ASK, that's when we have high, this means sine wave F2, the carrier frequency 2 and carrier frequency 1 is depend on, that means the carrier frequency 1 is low and carrier frequency 2 is high. So after that is multiplied together, so we will have the FSK. So this is the first method, same as to get the FSK, same as ASK. You can generate the FSK by multiplier. But this one is another one is summing amplifier. So this is to add the first ASK and second ASK. So this is the first multiplier. And for the second method, by using switch, same as ASK, but for this one, is if the switch is closed, okay, because this have the FC1 and FC2. Okay, if for ASK, if open, the carrier can go through it. Close, carrier cannot go through it, so it's only straight line. But for FSK, if switch is closed, FC2 will operate. And if it's open, FC1 will function. This means is the even if same method by using switch, but for ASK it's only have one carrier signal, but FSK we have two carrier signals, so the operation of the switch is a bit different because both, this means if close and open, both carrier will go, this means both will have the output but different output based on the selection of the carrier signal. Okay, and the third method to generate the FSK is using a device known as VCO. Okay, because this VCO, it can change the frequency when the amplitude of the voltage is applied to it. Okay, for example, okay, when because we have this is actually VMT. So okay, VMT we have in 1 and 0. If the voltage is 0, it will produce a frequency, and if it's 1, voltage is maximum, then different frequency will be generated. So it will produce frequency 1 and frequency 2. So this is how the VCO function. And before go through the VCO, it go through the low pass filter, where only low frequency will go. This mean only because this is considered the low frequency. So any higher frequency will be to receive it. There are two method. There is asynchronous and synchronous. So for asynchronous, it's use to filter to tune to two different frequency. So this is a filter. Okay, this is filter 1 and filter 2. Okay. Okay, for FSK, the signal is like this. It's, we have FC1 and FC2. Okay. And for after go through the filter 1, this means the higher frequency will for example here the FC1 is higher and FC2 is lower. So it will only pass through the high frequency. Let's do this plus right now. High frequency, but not pass through the low frequency. And the filter 2 is it's minus, so it's lower. So for first is not the high frequency is cannot go through, not allowed, and then pass through the low frequency, and it will go through the logic comparator. That means if it is high, it will become 1, low become 0. So that's why for after logic, it will just come like this, 101. It is for the asynchronous, and for the synchronous, okay, for this one, compared to asynchronous, for synchronous, it go through the low pass filter. It's been almost same, but for this one is for asynchronous use logic and synchronous use low pass filter. Okay. Okay, same. Okay. For the noise, is different based on the receiver. How the signal is received, the noise is depend on the receiver. So for the asynchronous, the formula for the BER is half of exponential of negative EB over 2NO, and EB same as before, but synchronous same as ASK. That is, the formula is half. That is a bit different. Okay, for ASK, the PE is equal 1 over 2 ERFC EB over 4NO. Okay, but for synchronous, it also have ERFC, but the inside square root is a bit different. So this is formula for the noise by using asynchronous. They have the low pass filter. Using asynchronous have the comparator. So I think the formula will be given in the sheet, but you need to understand how it's used. Okay. Okay, before we end, we can try first this question. Okay, for this question, it is a asynchronous FSK system. So you need to use this asynchronous. There is a half E power of negative EB over 2NO. BER is half E power of negative EB negative EB over 2NO. So the given here is okay, for 10 megahertz is frequency. It's same as okay, some of the parameter is only given but it's not used for the equation. So this is delta F. Delta F is will be used if it's asked for bandwidth, because the bandwidth is the formula of bandwidth, the FB plus 2 delta F prime. FB plus 2 delta F. So this is the delta F, and this is the frequency. This is FM. That's for if us about FM also can use this, but for this question no need. And the bit rate is 110 bits per second. Okay, bit rate here is to get the T. So T is equal to 1 over 110. The peak to peak carrier signal is 2. So ECC, the carrier signal, the EPP, peak to peak is 2. So for EC is E peak to peak over 2. So from here you can get the EC. And noise power spectrum density for 2 band. Okay, for 2 band, so this is the value of NO over 2. So this is the value for NO over 2. And okay, from here we need to know the EB. Okay, the formula for EB is EC squared T over 2. And EC here is EPP over 2. EPP is 2 over 2, it is 1. And T is 1 over 110. It is 9.09 power of negative 3 over 2. Okay, so after you calculate it, you should get 4.55 times negative 0 of negative 3. Okay, this is EB here. And then NO over 2 is equal 1 times 10 power of negative 4. So NO is 2 times 10 power of negative 4. So EB over 2NO is equal to 4.55 times 10 power of negative 3 over 2 times 2 times 10 power of negative 4. So you should get the value here is 11.38. So 11.38 is here. So BER is equal 1 over 2 E negative 11.38. 1.38. So you should get the BER is 5.7 times 10 power of negative 4. This is the answer. Okay, any question for this question?
No, doctor.
Okay, so if not, just try example 2. This means this is the homework for you. Same question, but for the asynchronous, and compare the BR. Okay, tomorrow. Next week, we will proceed with the third digital modulation. That is phase shift keying. Okay. So for today, any other question? Okay, for okay, yesterday one of you has asked about the block diagram of generation and detection of PCM. Why is have parallel to series and series to parallel? And it is because when it is encoded, it is in parallel signal. So that means the encoding encoding after go through the encoding to get the PCM pulse modulation, it is considered as a parallel signal. But if we want to send through transmission medium, it's need to convert into series to go through the transmission signal, a transmission medium. But it's convert back to parallel because the real pulse code modulation is parallel. It's been the encoded before it's change digital to analog converter, is convert back to the parallel. This means the parallel to series to parallel is because we want to transmit the signal by using the medium transmission, where the medium transmission only allow the series signal. Okay, that is the why there are parallel to series and series to parallel for yesterday class. Okay, for this class or what? If anything related to this subject, any question before we end the class? Okay, if not, just okay, we can end now. Anything I will